Actually, this the time to start our session. I'm Wang Chul Song, chair of this AI-driven networks working group. And our co-chair is Hidehisa Nagano from NICT. He's here. And Jiahong Huang, Professor Jiahong Huang from BUPT of China will join virtually. Then I will chair the first session, and in the next session, Dr. Hidehisa Nagano will chair the second session. We have two sessions, and the first session has these presentations. Also, in the second session, we have also four presentations like that. Then, actually, firstly, Mariam and Chin will present the first presentation, but Professor Huang has requested me to change the order of the presentation talk. Then also he.
I'm online now. Hi, Professor Song.
Now, can you show him? Can you show him?
No. Yeah, yes. Yeah.
Okay.
Hi, Professor Song.
Professor Han. Then we have the full presentation. Then you can speak during 20 minutes, and you can have a question and answers. Okay.
Okay.
We can then let me start our session. Then the first presenter is Professor Han Zhang from Tsinghua University. His title is presentation title is AI ML technology in network DevOps. Thank you. Please start.
Thanks, Professor Song. Thanks, Korean for my mistake. Okay. Oh, I can't share my screen because some others are also sharing the screen. Please close the screen. Yeah. I can't share my screen now. Sorry. Hi, Professor Song. Can you close the sharing of the screen? Okay. Oh, no. Okay. No. I still can't share the screen.
The screen is shared.
Yeah, it's okay. Can you see my screen now?
Yes, but there's no content.
It's okay now?
No.
Okay. Hello everyone. I'm from Tsinghua University. Today my topic is
it is not shared.
Can you see the screen now? Okay. My topic is AI machine learning technology in the network DevOps. Today my topics includes the following three aspects. The first is that I will introduce some network problem. The second, I will introduce the advantages of AI in network DevOps. Then I will introduce some practice in AI. Can you see the screen now?
Not yet.
No. I can't. Wait a minute, please. It's okay now?
Not yet. I'm sorry. Just wait for a second.
Okay, it's okay now?
It's okay. Thank you.
Okay. Then I will introduce some practice about DevOps. It includes about two aspects. The first is that network optimization. It includes how to apply AI in network planning and traffic engineering. Then I will introduce failure events detection and malicious traffic detection on network troubleshooting with AI. Now I will introduce some problem in our practice. The network is in inefficiency state. Pro-efficiency average utilization over time or busy links is only 30 to 50% across the management of Microsoft. The pro-sharing little support for flexible resource sharing. We can see from the two pictures. The second problem is that the network is vulnerable to faults. The faults mainly come from two aspects. The first is control plane faults. For example, it includes firmware bugs, memory shortage, or failures or long delays to configure network device. Also, we can also have some data plane faults. For example, link and switch failures. The third problem we may have is that we have some security problems. The left picture is reporting the network security events from CERNET. We can see that the attack number is increasing sharply from 2018 to 2021. Also, the cybercrime is also increasing with the use of the internet. Now we face the efficiency, security, and availability of the internet, so that what we can do to optimize the network. Fortunately, we have AI. AI has the true advantages in network DevOps. The first is that we can use artificial intelligence and other technologies to make machines that can make data-driven decisions much faster than humans. The second is that data may be as a base for optimizing network management. Customer experience, service assurance, include incident management. So the second is that AI is zero human rest. It is obvious that machines don't get tired. Machines can work endlessly without breaks and don't even get bored doing the same thing respectively, like a human. It's not like a human. Now I will introduce some practice with AI to optimize the network. The fourth is that we can use AI on network planning. Under network planning, we have many critical steps in decommissioning the backbone to satisfy the operational requirements. For example, the operators or the customers we have SLA. It is very hard to build the network with low cost to satisfy the requirements of customers, since the network is always closed layer, because we have to optimize both IP layer and optimal core layer. Also, when we plan the network, we face the short-term plan and the long-term plan. Also, the network may fail, so that the reliable of network and the availability of users should be considered. For example, this is a topology of a network. We have 6 sites, and the fiber and the sites has many fibers, and we have 100 Gbps from set A to set D under several single fiber failures. We have 2 planning options. The first is short-term planning, and the second is long-term planning. If we choose the short-term planning, that we only need to add 2 IP links to satisfy the 100 Gbps. Also, for the long-term planning, we should consider the more failure conditions that we should add a fiber to satisfy the long-term planning. Also, we can use the machine learning or deep reinforcement learning methods to help us to make the decision. For example, we can input the traffic demand and network topology and failure scenarios and reliable policies and even cost model to optimization model. Then we can use deep reinforcement learning to solve it. And after that, we can output the IP layer and the optical layer mapping. Also, we can also use AI for anti-traffic engineering. Also, users have SLA in their call more rigorous SLA. For example, however, the network may fail at any times. When we perform traffic engineering, we should consider the failures into consideration. For example, we have a bandwidth demand from set A to set D, and how we should configure the network to satisfy the deep demand. The promised also the promised bandwidth and the services always have availability requirements, and we should also take the availability requirements into consideration. But we can use we can build a linear optimization model to solve the problem. For example, we can build a automation control algorithm, and then we perform traffic scheduling and failure recovery steps to satisfy the demands. For example, we can build a linear optimization to optimize the bandwidth allocation periodically. Then we model the problem and the LP programming. We can also use the AI to reduce the solving of the problem. Then we also implemented under one traffic under one controller. The results show that the method performed well. Also, we can also AI enter network failure detection. For example, enter BGP failure detection. BGP as the infrastructure of cyberspace, and it is the base protocol for network interconnection and plays an important role in internet operation. BGP encounters some failures and malicious attack. The selected path of the interdomain routes will change. The destructive route change events will interrupt the connection of application services, which will seriously affect the network and service performance. For example, we can use AI to detect the failure of BGP. We can use the 4 steps. For example, we can collect the BGP message collection. Then we will build the region level exact features. Then we can use the AI model, for example, a decision tree to detect whether there is outage. And last, we can also use some AI model to diagnose the root cause of the BGP outage. And last, I will introduce our practice about malicious traffic detection. For example, we have SD-WAN. It is a virtual architecture that enables enterprise to securely connect their branches using the internet or MPLS. We can also use the similar model as BGP detection. For example, we can collect traffic and perform traffic cleaning, and then form the flow vector generation. Then we can use some flow feature exaggeration methods, and then feed the features into an isolation forest model. At last, the model will output whether the traffic or the flows have malicious behaviors. We also implement the methods into a real network, the results show that AI performs very well and much better than other methods. So I think the time is reduced. So I think it is my topics can finish now. And AI is a good technology to optimize the network, and we can use it to optimize that. We can besides the introduction, we can also use AI to optimize other behaviors. For example, we can access the networks, and we can also use the AI for other aims. So and the AI model has many options, and we can choose the models according to the scenery. So AI has a bright future, so that we can recommend to use AI enter more areas, include besides the introduction of my talk. Thank you. Any questions?
Thank you for your presentation. Any questions?
Thank you. I'm Muhammad Suleiman from Jeju National University.
Thank you.
I was actually wondering, you mentioned in your presentation that AI mechanisms can take decisions fast.
Yes.
So, to what extent they can take fast in a time series, data and mechanism, and can you elaborate this, please? Thank you.
Pardon? Sorry, my signal is weak.
Okay, I'll repeat the question. AI mechanisms can take decisions fast. So my question is how fast and to what extent they can take decisions fast. Can you elaborate this?
It is a good problem. The question, the use AI, it is not an online manner. Indeed, it always an offline manners. The offline is, for example, different scenery has different time slots. In the traffic engineering, we use AI about 5 minutes interval. If the interval is larger, the accuracy is very low. If the interval is low, we can't get a good result either. So that the interval is hard to choice in practice. Also, I think AI, the best practice we use AI is to use the offline analyze. So for example, the anomaly detection to analyze net flow and traffic. For online detection, AI may perform worse than other methods. It is my practice. Thank you.
Just a moment. Can you keep sharing your screen? Actually, we can see your face, but can you share your screen? Can you share your the slide?
Okay. Can you see this?
Yeah. Then the another question is.
Hello, Professor. Sorry, too high. This is Javier Diaz from Jeju National University. This question is related to the network planning. That I think it was the first topic that you presented. And you mentioned some AI techniques that you are following, like deep reinforcement learning. So I want to know how you are evaluating the performance of the DRL, specifically in the decisions for the network planning in sense. as you were speaking about optical networks, fiber networks. So I don't know if we are evaluating physical deployments or we are evaluating overlay deployments that could be more automated and immediately reconfigure in the sense of planning the number of nodes and the number of links themselves. Want to know the exact evaluation that we're doing for the model itself in order to detect that if it's performing good or performing bad whenever there is a reconfiguration of the network.
Okay, thank you. So when I use network planning problem, we always use it to solve the model more quickly. We also use it the linear optimization method. What we care is that how the optical layer and the IP layer how they match together. For example, the IP link may pass multiple optical layer, and the optical layer may carry much more IP links. So that how they can match to satisfy the requirements of their customers. The model we use is also the linear optimization. The AI we use is just to solve the problem, because in a complex network, there are many states. It is very hard and slow to solve the problem. We just use the AI to solve the problem rather than just use AI to output good results. Maybe in the future, a more complex AI model can do this. But now we think that the traditional optimization methods may be a better choice. Thank you.
Thank you very much, Professor.
Any other questions? Actually, too many questions. And then actually, I have one question, a very simple question. You mentioned the SD-WAN. Then do you have any project for the SD-WAN, especially for the deployment of the SD-WAN?
Yes, we have. In the future, this is our work. In the future, we will make it open source. You can pay attention to IEEE tips journal. This is one of our recent works. So you can pay attention to this, and you can also mail to me if you are interested in the source code of our project. And yes.
Was it deployed in a real network?
Yes, we have deployed.
What kind of network have you done it?
Yes.
What kind of network?
We deployed it. We do this with and cooperate with a company. We perform it on a bank company. It about have 10 nodes. This is our practice.
Okay, thank you.
Thank you.
Please applause.
Thank you so much.
Then next, I'm sorry. Can you change the screen to my system? I'm sorry to trouble for sharing the screens. No. Yeah. Okay, then the next speakers are Mariam Kiran and Chin Guok from ESNet. Then I think Mariam has connected to our stations. Is there, Mariam?
Yes, I'm here. I can start sharing screen.
Okay. Our presentation title is using AI to improve traffic engineering for science networks. Kate. Okay, then please share the first screen. Zoom screen. You need to share the Zoom screen.
You see my screen?
You can start. It is properly shared.
Okay, and you guys can hear me okay as well? So mic check. Can you hear me okay?
You can start, please.
Okay. So thank you, Song and everybody for inviting us again. So hopefully next time we'll be there physically. So we're talking about this tool which we're developing called Hecate, and I'll tell you why we're calling it Hecate as well. But we're trying to do traffic engineering on ESNet, which is a science wide area network. So we're trying to use AI to actually optimize this. So I'm Mariam Pirin. I work as a research scientist at Lawrence Berkeley National Lab. So we're trying to do this on the DOE Science Network. So our problem is driven by bringing AI to control plane. So ESNet is a science RNE network, which means that we have to provide guaranteed user experience to the diverse sciences which are using our network, such as no packet loss and high throughput. We also want to improve the overall network performance for better using our facility. We did a study and it turns out that at one time, only 40% of our network is used to full capacity. So we are thinking of ways on how we can push that up to 100. So this particular project focus was to improve traffic engineering to allow this multi-objective path optimization for these different sciences. And what we're doing is we're putting an AI agent onto the network, which learns off of historical data sets and the topology of the network, and it tries to predict and readjust the network based on what it learns. So our goal is to have more transfers, less congestion points, and better quality of service. So we're pitching this idea under the self-driving networks. So I think the talk before was very interesting because the speaker spoke about so many different ways in which you can use AI. Our focus is only on traffic engineering here, but this is what our networks look like today. So we have static routing algorithms using shortest possible route, for example, which we all know leads to congestion and packet loss. And we are heavily invested in exploring different TCP algorithms to know which one is better for science. And our process is very reactive. So something goes wrong on the network, then people wake up at 3 a.m. in the morning and they try to make sure everything is working right. So our vision is to have adaptive routing so that real-time routing decisions can be made. An AI agent or a network can learn to avoid congestion. So if it predicts that there is going to be congestion on this particular link in the future, it's not going to use that link and divert the traffic somewhere else. And pushing the network to go hotter, so 100% utilization, and be much more proactive. So this is where the prediction part comes in. The way which we're doing it, ESNet is a very large network, and this is the wide area network, which the diagram which I have at the bottom. It spans from California. So if you can see my mouse, this is where we are right now, Berkeley and NERSC, going all the way to the top of the United States. And we cross across the Atlantic, going to London, Amsterdam, CERN, which is located in Switzerland. So we manage all the links across over here. So when a scientist runs an experiment on CERN, they actually use ESNet to send their data back to NERSC, for example, for any analysis done. So we provide high performance throughput with low loss for this very sensitive data transfers. We also have to keep in mind the latency. So we're also exploring cloud. For example, if you want to burst onto the cloud and do some engineering over there. ESNet has developed their own tools to actually do this dedicated network patching, which is called Oscars, is one of the very famous tools, and it's been in use for a few years across these networks. So that's available to download if people wanted to explore it within their networks. And we also partner with other networks such as the Asia Pacific networks or Janet or Giant in Europe, for example. So, this graph actually shows you how our data volume has grown over the last few years. Initially starting off from 1991, and the pandemic took a little bit of a hit, but we see like an exponential growth in data as we go forward. And part of this traffic is driven by Large Hadron Collider traffic, which is the physics experiments which are running in Switzerland. And if we don't change anything in the network, eventually we're going to run out of space. So that means either you spend more money and buy more bandwidth and more high quality hardware, or we try to use what we have to the maximum and then upgrade the network. So there are two different schools of thought in this particular area. Talking to network engineers, they prefer to just buy more hardware. As scientists, I'm much more inclined to see how we can get more out of the resources we already have. So ESNet did a very big rollout of ESNet 6 over the last few months. So there's just a slide to show you what new capabilities were added. And this kind of shows you what AI can be done. So we actually upgraded the network to 400 gig now, and we have integrated telemetry. So we're collecting real-time monitoring data off of all the routers and switches present on the network, SNMP statistics, persona statistics, and they all go into this live dashboard, which we can hook into and get live performance of how the network is going. We're also writing network automation tools where we've written tools like notebooks and stuff where you can actually roll out changes on the network by hooking them into network resources as well. Now, an important part of this rollout has been the new concept of segment routing, which we have introduced is traffic engineering capability. So it's basically working with the Nokia devices where they can put in a segment routing which is a PCE controller, and they can define their rules in that. And that PCE can then go in and do changes on the network as required. And it's very fast to react. So that reaction takes very, very quickly. But the PCE in itself is very dumb. So you tell it what to do and it will actually go and do it. So that's where we want to put AI, that AI can then communicate with the PCE and then the PCE can do changes. Other RNE networks are also developing similar technologies, and it's this kind of venue is very good because we can learn off of each other and exchange code, data, for example, etc. So the problem which we are doing again is how to use the network much more efficiently and run it much more hotter in our terms. So basically have more data, have 100% utilization as the network grows. So we also look at this as an optimization problem because every science flow, which could be an elephant flow, which are the big data transfers, or the mice flow, which are the small transfers, they can have different requirements on the network. So how can we do bespoke networks for those particular flows? And the solution which I'm developing is called Hecate. And Hecate is actually the goddess, the Greek goddess for black magic, basically. So that's why we're trying to do black magic on the network, and that's why we named it Hecate. We're using deep reinforcement learning. So we have an agent which basically sits and observes all these telemetries which are coming off of network, and it reads that in as a state. It can then do actions on the network, and then based on that, it gets a reward. So over time, it learns what to do. But there are more aspects of this deep reinforcement learning, which is coming in the next slide. So basically, just to drive in this idea of how the state is read in. So for example, if we have a 4-node topology network here, and we have flows that are flowing from A to D, you can read in the state of the network, which is basically the monitoring data which you collect off of that network at that particular time interval. And that becomes your state in observation. And then you do an action, which is either you take the route via C, or the second action is taking the route via B. So you can then get rewards based off that. And as a mathematical problem, this is very nice because this immediately becomes a Markov decision process. And that means that you can then throw in all the optimization algorithms, which we have learned over the years, once it is defined as a Markov decision process. So Hecate has multiple elements to it. So it has these monitors, which we are hooking into the network telemetry. So these are also called edge systems. That has talks to our AI and machine learning components here. We have a simulation agent because that is where the deep reinforcement learning will actually simulate and learn what the best strategies are. We also have a traffic class identifier. So this tries to identify if it's an elephant flow or a mice flow and can do per class optimization. So the conductor, we're calling it the conductor, is the one which changes, which does the optimization. And then in the future, we want to put in real time and fault tolerance. So these are future aspects. A lot of this work is developed using PyTorch. So we're still working on this. And then that particular element of Hecate can then connect to PCE segment routing and also other SDN solutions, which can then essentially go and do changes on the network. So I spoke about the conductor versus orchestrator. So where we think Hecate does more than just an orchestrator, network orchestrator does, because it actually does data-driven learning as well. So when I spoke about that, we're learning the state of the network, we're actually learning 3 different things. So we learn the topology of the network. We learn the real-time telemetry, which is the network health data. And then we also learn what kind of traffic classes exist. So we learn that 80% of the traffic is elephant and 20% is mice. So the reconfiguring of the network will be heavily optimized for elephant flows. And this can be done dynamically based on what the traffic is looking like on that particular day. The reward is to optimize for average utilization, latency, and the used links, because the more the links are used, the better the utilization is. So we've halfway through developing this, actually. So we have the NetFlow data, the persona data, and other data sources all coming into an unsupervised cluster analysis. So this is what actually does the traffic classification, identifies how much of elephant and mice flows exist. And we can add much more other kinds of classes, like these are important classes that need to be sorted out earlier. Then we use graph neural networks actually to do predictions of what the future values are going to look like. So this takes the network topology in as a graph, takes in the real-time network health data, and predicts the future. So it predicts where congestion is going to happen in the network. All of these values are fed into the global optimizer. So it takes in, this is what I am predicting, and this is what the current traffic analysis looks like. And that feeds it into the path computation engine to tell the routers what are the decisions and how you want to update their routing tables. So identifying traffic classes are done in 2 ways, either looking at site characteristics or link characteristics. So we look at jumbo, which are the elephant flows, interactive flows, and default flows, for example. So these are, for example, we know that we can identify between LHC, which is a Large Hadron Collider, and Berkeley, there's always like 80% elephant flows. So we can then optimize that particular path with that. In link characteristics, we can optimize for loss, delay, and jitter. So this is real-time time series data coming from Persona. And there are arguments that you can add more data like S-flow or other kinds of data sources when they start becoming available on the network. This is the graph neural network. So basically what it does is it reads in the network topology. So this is the same 4-node network topology I started with. And then it has like these triangles, which give you blocks of what the health data is at that point. And the health data includes loss, latency, and delay. And it uses that, feeds it into the graph neural network, which is a spatiotemporal graph. And then it predicts into the future. And we can define like how many time steps into the future we want the prediction to be. Obviously, the more future you predict, the worse the error rate is going to be. But it's something where at least the first few time steps, you can still get a good prediction. So we're still exploring this idea. So this is what happens. You take a network state, which reads in the network health, traffic patterns, the nodes and the features are fed in the graph representation. Then you do link prediction. So you're predicting what the links are going to be in the future. And then you do a greedy search, is where the optimizer actually sends back a discrete solution for how the network needs to be optimized. So we're using AI in different ways here. We're using prediction, graph neural networks initially, and then we're using deep reinforcement learning for the greedy search and optimization, which we're doing over here. And you can also set different reward functions you want. So if you want to optimize for loss, latency, jitter, or utilization, the users can set that in the beginning of running this experiment. And then the AI takes that as a reward function and tries to optimize for those. But this all comes down to the brains of what can actually be done on the network. So the PCE is a very core component of this. This has been kind of like a point to see even if we can do certain AI on the network. So we're exploring how PCE actually defines the netcog and the other rules and how it communicates to the routers. And once we've figured that out, we can use MPLS and stack labels to actually create those labels when the AI will push the decisions to the PCE. So I think going through this process, it's really important to identify what kind of rules exist and what rules can be generated, because then we can back work that the AI will be outputting those rules in that way. So this has been we've finally figured it out, so it's possible. So right now we're doing it with PCE, but we can render it with other tools as well. So for example, we've been testing this out in simulation because ESNet makes us test out everything in simulation before we push it to production network. And we have a current state of the network here. We ask the user what they want to be optimized on. And in this particular case, the AI reads in, it recognizes that the traffic classes have 50% of elephant versus 40% mice and 10% unrecognized. And then Hecate will run 100 flows for simulate, and then it trains, and then it allocates the graph. So this is the network topology which we've been testing with, and we simulate traffic and data on this. This is the kind of results we've been getting. So before, where we saw that there were certain links which were overused, like link 4, and some things were not used at all over here, like 0%. After Hecate ran, it actually gave a better distribution of traffic, like link 4 was less used, but there was more distribution across other links as well. So there is a lack of simulation platforms to test Hecate. We've had to write our own. So if there is in the community, that would be very good to share. I think there is challenges in data gathering and intervals used, and we are leveraging the traffic prediction algorithms, which have been written and published quite a lot. So a lot of the code is open source, but we're also packaging it up so that it can be one turnkey tool that you can take and install on your network, and then it will just work. So currently we're testing it with network engineering tools. And I think this is my last slide. So if anybody has any questions. And I think I don't hear you.
Okay. I'm Mohammad Suleiman from Jeju National University. Question is regarding perf sonar.
Yes.
Yes, for collecting data. So first of all, my question is that after collecting data, are you storing this data in some time series database, like with some timestamp? and what exactly time series database is used. Also, another question is that how frequently this data is being collected? Like for how long this data is being collected? Thank you.
Okay. So yes, Profsonar data is being collected. So the telemetry system, which ESNet has developed, it's currently hosted on the cloud. I think it's Google Cloud. So they've built a very intensive database, time series database collection system where you can actually backtrack and see what Profsonar was looking like in the past. I'm not sure how far behind they are collecting. I think a week. It is collected and it is stored in the cloud. The other part of the question is, so Profsonar can be set to collect data at every 5-minute intervals. So when we run our machine learning, for example, we are more interested in hourly data. So we take those 5-minute intervals and then we jumble them up to 1 hour. And then that's what we feed into our machine learning algorithms. So you can collect data at any time interval. So 5 minutes is okay. And our argument is that we're only doing traffic engineering once a day. Like once a day, Hecate learns what is happening and then reconfigures the network. So we're more concerned with hourly predictions in that case.
Thank you.
Hello, Kiran. I am Amar from Jeju National University. My question is regarding the QoS requirement. You are collecting the elephant flows, but there are different QoS requirement for like file transfer and different for video streaming. They are different actually the requirements. So how you are actually tackling these things, because they are all fall in the elephant category flow. So are you actually classifying these as well or not? That's my question. Thank you.
Yeah, no, it's a good question. So, so this is why we added that capability that Hecate will ask the user what they want to optimize on. So, for example, if it's a video kind of transfer, the user can say that I want to optimize on latency. So then it will take that as one of the optimization factors when it's calculating the optimal, but it will still classify them as elephants. So again, the way the classifier works, it's only looking at file size and the end time of the flow to predict whether this is an elephant flow or not. So we can set different optimizations for the different data sets. But it's a good question. I haven't thought about that, but we'll look into that further.
Any more questions?
Thank you, Miriam, for the excellent. This is Alexander van der Heel from SURF, Netherlands. If I'm not mistaken, on ESNet 6, you're using the network orchestrator. How do you see Hecate in relation to the network orchestrator, and where do they interact and where not?
Yeah, so this is being planned to be rolled out for ESNet 7 or 8. Currently, yes, it's not going to talk to the network orchestrator in ESNet 6, but we're testing out the PCE for the future, and it's going to talk to the PCE instead.
Like the network orchestrator themselves as well?
Pardon?
The network orchestrator through an interface also talks to the boxes directly, right? So aren't you planning to integrate those two, or the intelligence that you're building now to build it in the orchestrator or something like that?
So I'm currently focusing on doing this as part of PCE, but I've not looked at the network orchestrator yet.
Thank you.
Hi, Mariam. Thank you for your presentation. I wanted to ask how scalable do you think Hecate is when it comes to topology? Because you showed the topology which had, I think, 5 or 6 nodes. So if we talk about actual ESNet, so how scalable do you think the Hecate is in this case?
So it can be very scalable. So I've been exploring actually running the AI on Raspberry Pis and FPGAs to actually make it run faster as well. So that's a good question. So, for example, we've been thinking about using topologies. For example, Facebook and Microsoft, they have even larger topologies. So the problem is in graph neural networks, it all has to come as one graph. So in order for that to run quickly, either we have to run it on very fast hardware, or we have to find parallelization techniques, which I think the machine learning community is still developing on how to parallelize graphs for learning. So right now we're exploring on changing the hardware just to make it much more, to run it faster and training faster.
No more question. Then I have a question, Miriam. Actually, I think your simulation result is based on the SDN-based architecture, but your network is a traditional. As far as I understand, your network is just a traditional network, and you plan to transform your network to the SDN-based networks.
So there is a plan for. So we are currently going into much more software controlled networks. That's why we've been developing this very high-tech telemetry and automation tools. So we've already done the first rollout in ESNet 6, but we see that ESNet 7 and 8, which is the plan for the next 10 years, is going to be much more software controlled.
I have done some experiment on Korean in Korea. Then in the case, there is some administrative problems when I try to make some control over the networks. Then they separate the networks from the original working networks. So I think it could be a very big problem to into the SDN-based network. So actually, if you have more plan to in the future, please let's share here working group.
Yeah, this is exactly the problem I'm having right now, because the network engineers don't let us touch the physical network. So they've developed their own test bed kind of tools where you can do testing of your software, but it will be a big mind change for them to actually turn the switch on. So that's something which they said, unless we know that it's working very nicely in the software setting, we won't let it transition into the hardware. So yeah, it's going to be a uphill battle, but yeah, it'll be interesting to learn from you guys if you've done that as well, to see how we can make things run smoothly.
Thank you. Thank you for your presentation. Please give her your hands. Okay, then we can go to the third presentation. It is from NIST. The speaker's name is Dr. Takahiro Hirayama. His presentation title will be ML-based network function management for service function chaining platform. Is there Dr. Hirayama?
Yes, hello. Can you hear me?
Yeah, I can.
Okay. Can you see my slides?
You can start now.
Okay. Can you see my slide? So, okay. Okay, thank you for introduction. My name is Takahiro Hirayama from NICT. In this presentation, I talk about machine learning-based autonomic resource management framework for service function chaining platform. This presentation is organized as these topics. Firstly, I introduce our research background. In network function virtualization platforms, network functions are logically separated and placed over the network. Service function chaining is one of the techniques of the network function virtualization. Service function chains are constructed by a series of virtualized network functions. They are placed on the path from server to the end host. Each packet is forwarded to users with being processed by each BNF. By doing so, SFC operators can provide resources flexibly and efficiently to diverse network services. This figure shows an example of an SFC. Packets go through these function components on the path. Physical infrastructure provides computational resources to BNS, such as CPUs, memory, and so on. When resource competition occurs, when resource competition occurs, some functions should be migrated to the other servers. Those have sufficient resources. To maintain quality of service of each chain and to keep using resource efficiently, infrastructure operators should react to changes of network conditions, such as cases when traffic suddenly increases or network failure occurs. In the future internet, many types of services will appear. A lot of network devices will connect, and service level agreement will become more diverse. So it will be hard to respond in a short time by manual operations or optimization, such as linear programming, integer linear programming-based approach. So we propose an autonomous resource management system for service function chaining platforms to adopt the changing situation in a short time. This slide shows an overview of dynamic control of computing resources for service function chains. We should maintain quality of service. For this purpose, we should use computing resources efficiently. Speedy resource adjustment is also needed. That is, judging should be in a few seconds. So we study autonomic AI-based control. This figure is a conceptual figure. Service function chains are consisted of set of virtualized or container-based network functions. Those process packets transferred on the path between server and client. In order to keep satisfying diverse quality of service requirements, we establish autonomic resource management framework. This framework includes two parts, monitoring AI and deploying AI. The monitoring engine gathers statistics of resource usage and traffic of each chains. By using the data, it predicts future demand by the regressor that has relearning framework to keep its accuracy. Regressors are based on an ensemble learning model, including long and short-term relearning methods. They keep its accuracy despite trend changes. And then the predicted demand is forwarded to the deployment engine. It includes functionalities of resource arbitration within the server and SFC migration scheduler over the network. Autonomic arbitration part allocate adequate computational resources to network functions according to predicted demands. If resource shortages can't be resolved by the arbitration, migration scheduler decides which and where network functions should be migrated, like this figure. This scheduler is based on encoder-recorder recurrent neural network. It solves a migration problem quickly with a small number of cells in the neural network. Next, I introduce the demand prediction framework for resource arbitration. This framework includes the ensemble learning architecture. To keep quality of services without performance degradation, dynamic resources allocation has a key role. The left figure shows the example. Traffic demands always changes, increases or decreases. When traffic arriving at a certain BNF suddenly increases, QoS gets worse if it has not enough resources to cover the traffic. To avoid the shortages, we introduced the agile resource adjustment. When the system predicts that traffic to the bottom BNF increases like this, the system reallocates resources to the VMF. In this figure, the system reduces the resource for the blue VNF and adds more resources to the orange VNF. Of course, this approach strongly depends on accuracy of demand prediction. So now we propose the regression relearning framework to keep prediction accuracy regardless of traffic trend changes. This slide shows the prediction framework based on ensemble learning model. By using multiple learning methods such as random forest or recurrent neural network, we attempt to achieve better prediction performance. This framework consists of weak and strong regressors. We assume multiple weak regressors are trained by the controller with the dataset gathered from the whole of network. The weak regressors are trained with the multiple datasets separated by some bugging techniques, and they are biased. The regressors are transferred to each server, and then each server selects the adequate weak regressors by using its unique strong regressor. It is based on Gaussian process. The server trains its regressor with the data gathered by itself. We propose a two-stage relearning mechanism for weak and strong regressors. They are called forgetting and dynamic ensemble. In the forgetting process, the weak regressors are periodically retrained with the data in the past few weeks or months. This process is aimed to keep up with the trend changes in long time scales. However, this process takes for a long time. So we also introduce a short-time training mechanism, dynamic ensemble. In the dynamic ensemble process, the strong regressor is trained with the data collected on the server in short time scales, such as in the past few hours or days. The process is done immediately when prediction accuracy gets worse. This process is designed for the adjustment of strong regressors to keep up the trend changes in short time scales. We evaluated the prediction accuracy against traffic arrivals of web services in our NICT website. We set the amount of CPU resources to be 20% larger than the predicted value. 20% means the margin. This figure shows one of remarkable improvements of relearning mechanism. If relearning mechanism is not included, the prediction traffic far from the real traffic. However, relearning mechanism improves the accuracy like this. This figure shows the probability of over and under provisioning against the 60-day traffic data. Totally, the probability of the provisioning error reduces about 45% smaller than the case of ARMA or RNN. We also tried to install the prediction framework and arbitration mechanism into the SFC platform. We developed the SFC platform according to these RFCs. We installed the arbitration AI engine and SFC manager. SFC manager controls an amount of resources, such as CPU cores allocated to each VNF. Arbitration AI engine monitors traffic volume arriving at each VNF and predicts its demand. When demand of service function 1 increases, the server increases the number of allocated CPU cores. The figure shows one of experimental results of resource arbitration. In this case, the number of allocated CPU cores is increasing as traffic demand changes. As a result of arbitration, CPU usage is slightly improved than that of its non-arbitration case. Next, I introduce network function migration scheduling method based on encoder-decoder recurrent neural network. This figure shows our framework of network function migration scheduling based on machine learning. This AI monitors sub-condition changes of demands and resource demand. And this AI quickly decides which function should be migrated, which sub-the function should be migrated to, and when the function should be migrated. This figure shows an example. Scheduling AI determines that VNF A1 should be migrated to server 3 at the time T1. This is because the VNF will be migrated frequently if VNF A1 is migrated to server 2, like this flow. This scheduling AI works to prevent resource shortage and frequent NF migration. We use a supervised machine learning model. So to train the AI, we have to get the optimization optimal solutions. So we firstly solved the network function migration scheduling problem as the integer linear programming. And then we train the AI with the obtained solutions. Today, I only show the objective function of the ILP. The constraint of the details of the constraints are described in our recent paper of CNSM. The objective is to minimize the uncomfortability function of each chain. This function is composed by 3 factors, G and M and L. G denotes the performance degradation caused by resource shortage. The value increases to total resource demand in the server exceeds the server's capacity. M denotes the performance degradation induced by the function migrations. The value increases when the network functions of the chain are migrated frequently. It denotes the performance degradation induced by latency between network functions. Due to time restriction, details are omitted. Please check our recent paper. By changing the coefficients alpha, beta, and gamma, we can set diverse QoS requirement of each chain. In this presentation, we use 3 types of services: expensive, moderate, and low. We use encoder-decoder recurrent neural network to determine the network function migration schedule. This model is suitable for use the time series data. The model reads input data 2 times by the encoder part and decoder part. At the first step, encoder guesses significance of each input, and decoder offers the solution. Decoder uses output from the encoder at the last step in this term, and output from the attention part. Attention integrated the output from the encoder cell at each time slot. Sorry. Input data includes server capacity and QoS requirement and resource demand of each function. We compare the performance of this encoder-decoder recurrent neural network, EDRNN, with optimal solution and runner placement. Training time was about 30 minutes, and validation takes only less than 1 minute. That is, the calculation time of EDRNN for one input data does not take a second. Comparing with optimal solutions, the degradation due to resource shortage increases. However, our approach is superior to random placement. This is because it avoids redundant function migration. The performance is 40% better than the random placement when we work focusing on expensive services. Okay. In previous, we focus on autonomic resource management by a single AI. However, in future, we should consider to manage the cases of multi-vendor environment by using combination of multiple AI. This is in progress of our collaborative research with Japanese carrier and vendor. This figure shows the workflow through these three AI: monitoring AI, and designing AI, and management AI. Monitoring AI detects a sign of failure before critical failure occurs. And then it notifies the possibility to the designing AI. Designing AI plans to reconstruct network services to avoid failure. For example, changing routes of some service function chains. The new plans are transferred to management AI. Our management AI to do the resource arbitration among existing functions and migrated functions. We designed the interface of those AI according to Open API standardized by TM Forum. This is one of our progress of support the national projects supported by Ministry of Japan. Okay. Lastly, its conclusion. Today, I introduced some parts of our recent work. First, I introduced the demand prediction framework based on ensemble learning, including relearning technique. Second, I introduced the network function migration scheduling technique based on encoder-decoder recurrent neural network. In future, we improve our autonomic resource management framework that is aimed to forward network operation automation to higher level from 3 to 4 and more. We consider one of solutions to adapt complex use cases is cooperation of multiple AI created by multiple carrier on vendors. My presentation is that's all. Thank you for attention.
Any question?
Hello, TH, because your name is too long, so that's why I'm calling you just TH, okay? This is Saqib. I am from Jeju National University. I have a question regarding resource arbitration and SFC reconstruction. As we know that they are related concepts, and resource allocation is a key consideration with reconstructing an SFC. So when we are talking about having multiple services, how these two are helpful in achieving ultra low latency?
We consider these our autonomic resource arbitration technique for to accommodate multiple QoS requirements. One of the QoS requirement is delay sensitive services such as remote surgeons or emergency call to some organizations. One low latency is one of key part of the services. It's up to service type.
Okay, all right. Thank you so much.
Any question? Actually, you mentioned the several and the VNF and they are just network functions. Then what kind of network consider?
Sorry,
is part of the 5G networks, 5G network modules?
Yeah, okay. I introduce now only on the result of our experiment system. However, now we plan to this system to introduce installed on the 5G test bed and cooperation with some Japanese carrier or vendors.
Okay, then another some simple question is that you mentioned the long-term and short-term. I'm wondering how far your ML model can predict. Actually, in time scale, I think according to the long-term prediction could be a low, less the precise due to that. If you have some criteria for the prediction in time scale, please let me know.
In this evaluation, we assume the prediction time scale is shown in this figure. It's monitoring among the 60 minutes and predict is among the traffic arrivals among within 20 minutes. Firstly, we gathered 60-minute time traffic data and predict the about traffic arrival in 20 minutes.
You mean the prediction? You can predict some values after 20 minutes or 60 minutes?
Yes, about it is hourly traffic prediction.
Okay, thank you. Any other question, please?
Hello, this is Javier Diaz. I have one question. I saw in one of your slides that you are collaborating with NEC, Japan, and
Yes.
this AI-empowered system design. As far as I know, NEC is doing research, and I think they are going to release a platform for automatic configuration of networks based on like simple definitions, high-layer simple definitions. And these are translated into Tosca configurations, and then they are going into the network automatically. So, for example, if I want a firewall or I want a deep packet inspector or some load balancer in my network, I just map it in high level, and then automatically it will be deployed by the system that NEC is developing. So, are you, I mean, this SFC research and implementation that you are doing, is it integrated into this platform or is a different project?
Yes, sorry, please repeat the last sentence.
I guess it's your SFC research. I mean, this presentation that you provided, is it part of this automatic platform that NEC is developing, or is it something totally different?
No, our research is not included their 5G design platform. This is partly collaboration with 3 companies. These 3 AI engines is developed by independently. However, it can be collaboration via open API standardized by TM Forum. But this collaborative research is point is how can we coordinate the collaboration interface by using open API.
Open API, correct.
Yeah.
Thank you. Thank you very much.
More question? thank you for your presentation. Thank you. Please give
Thank you.
your hands. Thank you. The next speaker is the last speaker of this session, and he's No Ho Young from Code J from Korea. Are you there?
Yes, I'm here.
Okay, then his presentation title is Development and Demonstration of Autonomous Network Management Technology for Free Recognition and Optimization of Korean-based failures. Please start.
Are you showing my screen?
Yes.
Yes. My presentation title is Development and Demonstration of Autonomous Network Management Technology for Pre-Recognition and Optimization of Current-Based Failures. This is my order of my presentation. As the internet broadband network is activated worldwide, intelligent network situation recognition, and it calls for an autonomous response. In case of failure in a large-scale network, great damage occurs due to service failure. So the development of autonomous network technology is very necessary. In this R&D, we research autonomous network technology to recognize failure in advance, develop a system that can be handled self-recovery and self-configuration in the event of failure, and apply it to the current network. This R&D target is upgraded AI engine for detecting abnormal traffic for advanced recognition of network failures and expanded management scope. Development of self-configuration process based on the IP SDN for network route optimization. Laying the foundation for self-healing and optimizing processing of the network. And last, current network AI and NMS operation management function upgrade. Research and development of current-based autonomous network technology began in 2020 and established the foundation for self-restoration and self-configuration by 2021. From 2022, a self-configuration process was defined so that the network path could be optimally changed when abnormal traffic was detected in the IP SDN network. In 2023, it plans to analyze various alarms coming from the system and define and develop processes that can handle self-recovery in case of invalid alarms. Alarms generated by network equipment are only after the failure has already occurred. In order to recognize the failure in advance, the usage and traffic volume of the equipment are monitored. In other words, it is possible to prevent a failure by monitoring the overload of equipment or the amount of traffic generated before a failure occurs. Therefore, in 2022, the detection range of abnormal traffic was expanded from the subscriber section to the backbone section. In addition, a new E2E traffic analysis function was developed to detect equipment load rates and analyze non-conforming traffic patterns in the network. The self-configuration process was developed as follows. When detecting abnormal traffic, the operator was made to recognize it through control. The system provides the operator to check the history of previous actions on the equipment in which the failure occurred. If route bypass is required, the system provides an optimal routes list in conjunction with IPSDN. The operator selects the path to be changed from the optimal path list and requests a path change. At this time, the system requests a route change to IPSDN. The result of the normal route change is received and notifies to the operator, and then the operator records the action. This is system architecture of current IP networks and AI NMS. To explain, hardware is a gateway for data collection. pre-process for data pre-processing and normalization processing, data lake for storing big data, RCA engine, root cause analysis so-called, AI engine for anomaly traffic detection. It consists of a web server for control and monitoring. In IPSDN, 3 servers are connected to the switch and proof for path calculation is driven. The data collection items for 2022 are as follows, and the collection functions has been improved from the existing 5 minutes collection to 1 minute collection. Lists are port-specific traffic data for IPSDN equipment, splint day, syslog data, and CPU and memory. This is our main developments list. Development of linkage function between systems, development of self-configuration process based on IPSDN for network path optimization, establish of network self-optimization processing AI engine development foundation, upgraded AI engine for abnormal traffic detection for pre-recognition of major failures, linking of operational data with big data lake and dashboard development, and network operations management function upgrade. From now, I will explain the detail of our development. First, improvements in the linkage function between systems. In conjunction with current IPSDN, we have improved the ability to collect traffic and equipment usage information from the 5-minute unit to 1-minute unit. We developed it to collect syslog and sflow data in real time. After the collect data is stored in its own DB, and it links with data lake. In order to recognize failures in current IPSDN switch equipment in advance, we have developed a function to collect the syslog and provide an alarm through this. Gateway collects syslog from equipment in real time and forwards it to fault manager. Fault manager reads setting information for alarming from DB and creates an alarm. The setting information for alarming is registered by the operator through the UI. Therefore, it was developed to recognize failures in advance by alerting specific abnormal symptoms using syslog messages. Syslog-based fault alarm have developed a UI for monitoring as shown. The left side will be the syslog alert contents that coming up in real time, and the right side will provide the topology configuration. In the root collection server, which is connected with IPSDN switch equipments, the probe is developed and driven for calculating the optimal path. In the gateway, it communicates with probe to collect and store the optimal path of the IPSDN network. In the self-configuration application, the UI is provided for optimal bypass path list so that the operator could request a final path change. This picture is schematically illustrates the self-configuration process. First, when abnormal traffic is detected, an event occurs in the form of the ticket. Here, connection information between equipments, ports, and equipments in which abnormal traffic has occurred can be checked. Second, select the ticket and click the failure response button to provide connection information between equipments, a graph of the trend of abnormal traffic, a history of failover that occurs in the same section, and an email address for each person in charge to share the failure. Third, when click the optimal route change request button, the system will provide a bypassable list of optimal routes. Last, it was developed so that the end operator can bypass the processing by a specific route under judgment. In addition, the route change work was recorded and developed so that it could be restored if necessary. In addition, E2E pass information of the IPSN network is stored on daily basis, and this figure is a screen that can inquire the stored E2E pass data. Next, development of the AI engine to detect abnormal traffic. First, improve the AI engine which were developed in 2021. Second, expand the coverage of traffic beyond the backbone section. And last, development that traffic equipment's load factor correlation model. We studied clustering-based model as a way to improve AI engine performance developed in 2021. For the previous model, it was structured for each port of the switch device. So the number of models are increased and performance is so slowed down. Therefore, we studied the way of clustering the port that similar traffic usage. In the figure, ports with similar traffic usage were clustered in the current network, which could be divided into about 15 groups. Therefore, we increased the amount of data used for one model running, and we tried to increase detection performance by increasing the corresponding pattern of model. We compare the integrated model which clustered studied with clustering result and each model performance. In the figure, red is real traffic, yellow is prediction of integrated model, gray is graph of prediction of each model. In some cases, an integrated model predicts real traffic better than each model, but this is not a case in all cases. It requires a good classification of clustering applications. Therefore, we did not apply the integrated model because the cluster applied the classification problem and the predictive performance of the integrated model is not significant improved. Since then, what we have done is to improve the baseline 1D CNN-based architecture. Using the encoder and decoder created using the learning data, a compression vector extracted important characteristics of the input pattern was generated, and the value of the generated compression vector was input into the predictor to generate predictions. Therefore, we select the final LSTM-based encoder-decoder predictor structure. Major improvements are simplified the existing 5-hour pattern into 1 hour and adding the log processing and time variables such as weekly and minute units and etc. Improve the split processing, pre-processing way that inflow-outflow model. This figure is composition graph that prediction result. Blue is the real-time traffic, and red is new models prediction line, and green is the old model prediction line. The new model prediction has a smaller error range compared to the old model, and it is confirmed that the prediction error is slightly improved. This new model has been expanded to detect abnormal traffic for subscriber interval ports and backbone interval ports on the current IPSD network. And the function was expanded to detect the load of the switch equipment. Figure shows the monitoring screen for the subscriber interval AI model drive. It can check the model's operation status for each subscriber. Figure shows the monitoring screen for the driving of the backbone section AI model. Finally, this is the monitoring screen of the overall detection model by switching equipments. As of September 2022, the number of operating model was about 600, but after functional improvement, 117 models were operated to improve the performance of the system. In addition, we were able to achieve a lower error rates compared to the previous model. From now, network operation management function upgrade. Real-time traffic monitoring and history inquiry functions have been developed for operators can analyze abnormal traffic detection. We have developed real-time usage monitoring and history check functions for operators can analyze equipment's overload detection. We improved function that record the details of the operator's recovery from failure. In the event of abnormal traffic, it was developed to store the data net based on the time point and improve the function for download the data. Next is establishments of network self-optimization processing AI engine development foundation. As a development goal in 2023, we plan to develop a function to analyze and block unnecessary traffic for network optimization. Therefore, E2E data must be secured from traffic analysis, so E2E data will be collected in 2022 and stored in conjunction with the data lake. It was developed to collect E2E data on IPSD network using SFlow in real time and to inquire traffic statistics by application, subscriber, and country. We also developed a setup function for unifying traffic analysis. Figure is in the AI NMS, the monitoring dashboard, which regarding data association with big data lake. Therefore, it was developed to the monitoring the situation in which the data is linked. The future research plan is to develop self-healing process to improve operational efficiency. An invalidity alarm is an alarm that does not require operator action, typically due to frequent equipment on-off by the customer. We expect to improve operational efficiency by reducing manual monitoring through self-recovery processing of invalidity alarms. Therefore, we plan to implement the AI engine and self-healing process for classifying invalidity tickets. This concludes the presentation on the development and demonstration of autonomous network management technology for pre-recognition and optimization of current-based failures. Thank you for my presentation, and sorry for cannot taking a question. If you have any question about this system, please email to me. Thank you.